Hello and welcome to Sunday's edition of Cracking the Cryptic, where yesterday we did the highest one-star rated puzzle on Logic Masters Germany, which was an arrow Sudoku, beautiful Sudoku by Adam Jaziri. And Mark has suggested that we change tack a little today by having a go at another, it's clearly got arrows in it. It's called One Trick Pony. And it's by the constructor Arbitrary. And Mark said we should try this, or I should try this, because apparently this has given the testers the devil's own job. No one is very sure how to solve it. Now, having said that, I found it on Logic Masters Germany, and it has 4 stars, not 5 stars out of 5 for difficulty. And so hopefully it might be doable. I snipped some of the comments, which amused me. So hopefully you can see that. Blashik, who's an amazing constructor. Wow, that was one satisfying solve. And then adds a PS. By the way, I'd like to file a complaint. There was way more than one trick involved. So this, although it's called One Trick Pony, it's got something more complicated about it. Anyway, this is what I plan to have a go at in today's video. I don't have any birthdays to tell you about today. I do, yes. Paws the Sudoku Hunt, which has been so popular this month. The competition has now closed, and we're going to release the solution videos. They may even be up by the time this video goes up. So if you did get stuck, and I know many of you didn't this month, we've had so many new entrants to the competition, people who've never managed to solve any of our Sudoku hunts before, who have managed to solve this month's hunt. So Paws has done just an amazing job at creating something approachable, which is what we hoped for in this holiday month. But yeah, if you did get stuck, or if you do want to watch the solution videos, they are now available over on Patreon. At least they are imminently available. And that's all. So why don't we kick straight into it? Let's have a look at One Trick Pony and see what Arbitrary has in store. These are the rules. The rules are really short. Normal Sudoku rules apply. So we have to put the digits 1 to 9 once each in every row, every column, and every 3 by 3 box. Digits in cages sum to the indicated value, and a quick squiz at the grid tells us that none of these cages actually cross outside a 3 by 3 box. So we don't even need the rule about digits not being able to repeat within a cage. They simply cannot repeat. So those 3 digits sum to 17, as indeed do those. Those to 13, those to 22, etc. And digits along an arrow sum to the digit in the connected circle. So those 3 digits there, imagine these were 1, 2, and 4. 1 plus 2 plus 4 is 7. You'd write 7 into the circle, and that arrow would then also have to sum to 7. And that's how the rules work. Do have a go. The way to play is to click the link under the video as usual, but now I get to play. Let's get cracking. 22 cage in 3 cells. There are only 2 ways to do that. It's 5, 8, 9 or 6, 7, 9, either of which definitely involves a 9, so I will record that. And this arrow, we've just looked at it in the example. In fact, the same is true of that arrow, I've now noticed, but this must be at least a 6, mustn't it? Because even if we keep these cells down to a minimum of 1, 2 and 3, we'd still get the arrow to add up to 6 or more, so that must be 6. So must this one. Look, 1, 2, 3 cells there, so those are 3 different digits being summed, so that is 6, 7, 8 or 9. Oh, actually so's that, I'm now realizing, and so's that. Now this happens sometimes in the puzzles that we do, where you get 6, 7, 8, 9 in sort of the 4 corners of the grid. Now it is very likely these will all be different in the correct solution to the puzzle, and probably our job is to work out why. I mean, obviously whatever that is, it can't be repeated in those 2 squares. Often these puzzles come with a diagonal constraint, although actually now I'm seeing it, these 2 digits actually aren't on the diagonal, so that's not quite what we're meant to do. Let me just think about this. Okay, here is another this is a subtle point, which is probably not relevant. Ooh, I don't know. I don't know whether this is relevant, but I've just noticed it, so I'm going to show you it. Because when I was thinking about the diagonals just then, look at this. Ah! Or look at this, if I could actually draw it. Look at that line. And imagine the grid is folded along that fold, the red line, if that was a fold. Now, if we ignore some of the grid furniture in the bottom right hand side of the grid, so we actually, other than that cage, it's very symmetrical, isn't it? This pattern here and this pattern are identical, I think. Or is it? Oh no, it's not. No, it's not quite. No, I'm wrong. It looked symmetrical, but I don't think it is actually. Now, this is in a different position, isn't it? Yeah, I'm talking absolute nonsense. It just looks, for some reason, that looked to me like it was very symmetrically placed, but it's actually not. Okay, so forget that. Because, I mean, often, in fact, the reason I'm thinking about this is we saw this in yesterday's puzzle. When something is very symmetrical about the negative or positive diagonal, you can almost do half a puzzle, because anything you do on the on one side of the diagram, you can almost always just transpose that logic into the other side of the diagram around the line of symmetry. So I'll forgive my brain for having that thought. Right, so what are we going to do then? We must have to somehow, I mean, that digit, for example, and the same is true here. Whatever that digit is, where does it go in this box? Now, by Sudoku, it can't go in its own row, and it wouldn't make sense for it to go on its own arrow, because imagine that square was the green digit, then these two digits would both have to be 0, wouldn't they, to preserve the mathematics of the piece. So that digit goes in one of those 3 squares, and the same will be true here. This digit will go in one of those 3 squares. Okay, let's try 15, 21, 22. 22 is... Right, okay, I can get rid of 6 from this square, I think. Presumably that square as well, although I haven't checked that. So what I've done there is I'm trying to think about what the absolute minimum value of those blue squares is. And because these squares are all in the same box, that sort of has an additional effect, doesn't it? Because the minimum these cells could be in box 2 would be 1, 2, 3, 4 and 5, and that gives you 15 there. Now if the minimum of those 3 in box 3 is another 6 from a 1, 2, 3 triple, and that was a minimum of 1, then that adds up to 22. So the blue squares are at least 22. Now what would happen then if this square here was as big as it could be? If this was as big as it could be, these 2 squares would have to add up to 13. So if this was 9, these 2 would have to add up to 13. So how could this ever be a 6? If this is a 6, it's not possible to make those digits add up to at least 22. Because these would add up to 12, and this would have to add up to 10, and that cannot be a 10. So that cannot be a 6. Now what I don't know is whether that logic is the same. It probably, in fact it is the same, isn't it? Because those digits, let's make those yellow for a moment, there's 3 digits in box 7, there's 1 digit here. So it's the same logic. So this also can't be a 6. We can get rid of the colour there for the time being. Now, so if Oh. Okay. Okay, the comments are going to be full of people saying, Simon is a very silly person. Yes, you're right, but I didn't see what I'm about to tell you until just now. Right, I could have got rid of 6 in a slightly easier way, I've just noticed, because I can use the way I've just thought of to get rid of 7 as well. I'm sorry. Okay, the point is here that 6 and 7 only have one way of constituting their arrows. So imagine this was a 7. What's this arrow? Well, it can only be 1, 2, 4, and that could only be 1, 2, 4. And now I've got a problem in row 2. Because where are 1, 2 and 4 going in row 2? Well, they're not going in any of these squares, so they've all got to go in that little string of digits, but that digit is not capable of being 1, 2 or 4. And of course the same logic applies if this had been a 6. I didn't spot this. But that's great. Well, it's great and it's not great. It's not great for me because it's made me look like a bit simple. But now this square can't be 6 or 7, and this square can't be 6 or 7 for the same reason. That the geometry on those arrows is the same. I can't put 1, 2, 4 or 1, 2, 3 into that sequence. Now we might be able to get rid of 8 as well. Well, nearly. If one of these was 8, then the 2 arrows would have to be the different ways of making up 8, because it's the same sort of thought. If this was 8 and this was 1, 2, 5 and this was 1, 2, 5, then I'd have to put 1, 2 and 5 into these squares, and I can't do that. In fact, if that's 9, does it work the same way? Do these have to be different ways of making 9? Because I'm wondering whether 1, 2, 6 would work. 2, 6, 1, 2, 6. Well, it's closer, but it doesn't work. Let me show you. If it's 1, 2, 6, 1, 2, 6, then this would have to be 6, wouldn't it? And these would have to be a 1, 2 pair. But now I've got a problem with the 6 arrow, because the 6 arrow needs to be 1, 2, 3, and now I've got far too many low digits in row 2, so that doesn't work. Okay, so this is interesting, because we've actually discovered something now. What we've discovered is whether these squares are 8 or 9, the way that the arrows work is different. The constitution of these digits is different from the constitution of these digits, and the same is going to be true down here. Well, I don't want to use dark green. I'll use light green and red. Now, so okay, here's another thought. I don't know if this is relevant, but I'm just going to say it. Are there how many digits are there in common between purple and blue? And I'm going to claim the answer to that is 1. Now the reason for that is if they're given whatever this total is, if there were 2 digits in common between these arrows, then the third digit would also be in common, wouldn't it? Because that's the nature of numbers. If this was an 8 and 1 and 2 were shared between both the purple and the blue arrow, then the matching digit to make up the total to 8 would have to be 5 in both cases, and we know that can't be true. So it's not true to say there are 2 common digits or 3 common digits. Could there be no common digits? Well, the answer to that is no, and that's because the triangular number for 6 is 21. What do I mean by that? Well, imagine there's no digits in common between purple and blue. The minimum sum we could make purple and blue add up to would be if we included in their arrows a 1, 2, 3, a 4, 5 and a 6. Now those digits sum to 21, and 21 is, well, firstly it's not even, which is a problem, but secondly, if this is 8, these arrows should sum to 16. If this is 9, these should sum to 18, not 21. It's too big. So there is definitely 1 common digit between purple and blue, and that digit is then going to go in one of these squares. Now, I doubt it can go here because that's too big. Yeah, the common digit's going to have to be a low digit, isn't it? Because otherwise, again, this is going to blow up and get too big. 1, 2, 3. 1, 2, 3, 6. Yeah, imagine, okay, so imagine that the common digit was not a low digit. So imagine it wasn't a 1, 2, or a 3. Then it's at least a 4, which would mean that we could populate these arrows with 1, 2, 3, double 4, 1, 2, 3, double 4 and 5 would be the minimum. And that's 19, which is too big. So the common digit is a 1, 2, or a 3, and that's going to go in one of these squares. And the same logic is going to apply in the columns, and there's going to be a 1, 2, or a 3 in one of those two squares as well. I haven't got... why? I don't know why this is called One Trick Pony. Because there's definitely... maybe it looks like a pony somehow. That could be true, actually. I'm very bad at spotting. I could spot the arrow man yesterday. There's one digit in common. So there's one of these digits is a 1, 2, or a 3. One of these digits is a 1, 2, or a 3. They can't both go in the 17 cage because it would be too... well, we couldn't make this an 11. So at least one of them is here, is in this domino. You see, it's really, I mean, if you could prove anything about orange and green, orange and dark green, it would be really handy. Because of this sort of square relationship. So imagine that these were both 9, then you could take 9 out of both of those other arrows at the other corners of the square. And the holy grail would be if these were different, because if these are different, you have to take 8 and 9 out of both of those squares. Oh, well, okay, here's a very simple deduction, which is nice. That these two are not both 8. Because if they were both 8, where would you put 1 in box 1? That's a fair question. Because a 3-cell 8 arrow always includes a 1, because it's either 1, 3, 4 or 1, 2, 5. So there'd be a 1 on here, a 1 on here, a 1 on here, and a 1 on here. And there would be 4 1s pointing into box 1, and the 1 would have to go right in the middle, where it definitely doesn't deserve to be. So this is great, because what that means is at least one of these squares is a 9. And now, neither of these squares can be 9, because whichever one of these is a 9, and one of them is, it doesn't matter. It sees both of the other vertexes of the square, or the rectangle that we can draw. So, right, so now there is definitely a 1 on that arrow, there's definitely a 1 on that arrow, and there's definitely a 1 on this arrow. That must be true. Now, that's not saying there's definitely a 1 there, there's definitely a 1 here. So I feel like this might be able to, I might be able to rule out 8 from both of these arrows. If 1 was on there and 1 was on here, then that would be a 1. There would be a 1 there. Oh, I can't quite see it, sorry. I thought I might be able to rule 8 out from, well, both of these basically, but I can't quite see how to do it. So if there's a 1 in both of those, then that's a 1. There's a 1 here. But what does that mean? Oh, that means that... oh, hang on. Actually... Alright, here is a little point which is interesting. Which is that if either of these is an 8, the other one... Well, we just worked that out in a different way. Oh, Simon. Yeah, if either of these is an 8, you have to put 9 on the other one. And we sort of worked that out, but one way I've just seen that in a different way... The way I've just seen that in a different way is that if this is 8, because you put 1s here and 1s here, the 1 on this arrow would be there, and this would be a 2, 3, 4 triple. And 2, 3 and 4 add up to 9. So if that's 8, that's 9, and vice versa, which is, I think that's going to be the corollary of what we were looking at before with trying to put 8 on both arrows and it not working. It's just a different way of seeing the same thing. But this is tricky then. I'm not quite seeing why. So if they're either an 8-9 pair or they're double 9. Now if they're double 9, they're either an 8-9 pair or they're double 9. They're double 9. They're double 9. 9s get thrown around the grid. I can see that. But not in a way that looks terribly interesting, I don't think. Sorry, I'm sorry. I'm sure that there is a way that this is obvious to everybody. And I'm just trying to work that out. I'm not doing a very good job of it. On at least one direction, Harry Styles is... I can't put 2 1s in those squares. I know that each of these arrows has a 1 on it. I can't put 1s in both of those. So on at least one arrow, there is a 1 that ventures further afield. Let's just say it's up here. It might be down here, or it might be in both. But I just want to think about what happens if there's a 1 in one of these squares. And the reason for that is it's ruling 1 out of so much real estate. Then there can only be a maximum of 1 1. But I think I'm just proving the same thing again. I think I'm just proving again that 9 must be on an arrow. I think that's all I'm proving, because all we're really proving by the fact that there is a 1 in one of those squares, for example, is that you can't put 1s in there. So this arrow, the 2 arrows emanating from this circle, can have a maximum of 1 1 on them, because we could put a 1 in one of those squares only, but not here as well. And therefore one of these arrows would be 2 3 4, and this would be a 9 arrow. Okay, let's try it a different way then. What if that was double 9? Is there anything? Is there a problem? There are only 3 ways of making 9 from 3 different digits, and those ways are 1 2 6, 1 3 5, and 2 3 4. And we know that. So we know that there would be at least 1 repeat, don't we, between purple. If this was double 9. These couldn't be 4 different ways of making 9. And we know that purple and blue can't be the same, and we know that red and green can't be the same. So either red would be the same as one of these, or green would be the same as one of these, or both. And the other thing I noticed was if you did double 9, then there's a 9 down here, and there's a 9 over here. Actually, that's not 9, that's not 9, that's not 9. In fact, you get a lot of... Actually, that's quite interesting. Oh, is that working or not? Golly gosh, I mean, that's very, very, very... That is interesting, isn't it? That almost looks right to me. So what I'm now noticing is if I double 9 the two circles, I can place a lot of 9s in this grid. I don't know if I can place all of them, but I can certainly place some. I'm also forcing that digit to be a 1, which makes that a 1. Ooh, actually that's quite interesting as well, because that makes that a 1, because I can't put 1 in the 17 cage, so this would be 2, 3, 4. This is getting horrifically complicated, but it's quite weird actually, because you can actually almost see it. I can almost see what's going to happen. I can't quite see to the end of the logical sequence what it means. I can see that this becomes an 8 for what it's worth. Not only that, I can see this arrow becomes a 5 here and a 1, 2 pair. And in fact, I can tell you that that's a 1. That's a 1. I don't think I can break it though. I'm not sure. Where was it? I thought that was a 1 as well, didn't I? Oh, that feels... Hang on. No, this doesn't work. Okay, I can see. It doesn't work. You can't do this. Double 9 doesn't work. But it's complicated. It's actually beautiful, but it's very odd. It's very odd indeed. Now, does what I've just done in my head there qualify as bifurcation? I'm going to claim no, because I could see it. And I haven't put anything in the grid, and I can see it's broken. But it is incredibly difficult to see. Well, no, it's not that difficult to see. It's sort of the consequence of everything we've been talking about. But it does suggest that there's an easier way to see it. Now... Oh, let me just explain what I've seen, and we can talk about it. So what I've noticed is that if you do double 9 these circles, you get a really interesting pattern of 9s in the grid. The first thing is that think about the 9 in box 2. Again, we sort of talked about this earlier. You can't put 9 on its own arrow, and you can't put 9 in its own row. So the 9 in box 2 would be in one of those squares. And it wouldn't. And then we can ask, because the 9 in box 5 is also in columns 4 and 5, you can see that the 9 in column 6 now, where would it go? Well, it would have to be in one of those 3 squares. You can't put 9 on an arrow, because this would be at least a 10. And you can't put 9 in its own row. So the 9 in column 6 would be here. So this is the start of the journey I went on. Because you can immediately see that this becomes a 9 in box 9 now. So we've got a 9 here and a 9 here. And now, but you've got the same thing going on in box 4. This 9 is forcing the 9 into one of those cells. And now we ask, where does the 9 go in row 6? And you can see it's in one of these squares, except it can't be there. And we've just put a 9 in row 7, column 9, so it's not there. So you get a 9 in this position here, row 6, column 8. And that's in a 10 cage. And that's going to put a 1 here. And this is where it gets fascinating. Okay, because now we're going to switch in our minds and say, okay, ones. Ones are interesting digits, especially in a puzzle called One Trick Pony, actually. That's interesting. I hadn't thought of that. Okay, well that gives me some comfort that perhaps this is what we're meant to do. I'm not sure, but let me keep explaining. So, in my mind I could see this was a 1. And you can see, what's that going to do? It's going to put a 1 here. And what's that going to do in this box? Now this is it. This is, again, it's very suspicious, because the 1 is in one of these 3 positions, but you can't put 1 in a 17 cage if there's a 9 elsewhere in the box, because the other 2 digits would add up to 16 and have to be a 7-9 pair. So that makes this a 1, doesn't it? Now, this arrow can't have a 1 on it, so what is it? It's 2, 3, 4. Now, what's this square? Well, it's at least a 5 by Sudoku, but it's on an arrow that can't add up to more than 8. So all that can happen is that this is a 5 and this is a 1-2 pair, and you can see the order. And now we're getting into the realms where things are really getting difficult, because, and this might be where there's an easier way to see that the plot has thickened too much. Yeah, I mean, we worked out that this was a 2, 3, 4 arrow. We know from our earlier work this couldn't also be a 2, 3, 4 arrow, so the other ways of making 9 always include a 1 on their arrows, so there's definitely a 1 in this domino under this paradigm, and now the 1 that must exist on this arrow going horizontally is there. And this breaks it. And this breaks it, because now I can't put a 1 on either of these arrows, which means they're both 2, 3, 4 arrows, and that absolutely higgledy-piggledies box 1. It makes it impossible to fill. So what we can say, I mean, is that fair? I mean, I could see it. I can see it, because it's about tracing the 1s around the grid. Well, it's about tracing the 1s round after you've thought about the 9s. But I'm not convinced that's not necessary in this, because it's so beautiful. The way, if you think about double 9, the way it forces the 9 here, it forces the 1 here, forces the 1 here, forces the 1 here, forces this arrow. It forces everything. It forces everything. It forces everything. It's beautiful. It really is. It's very clever and very beautiful. Yes, in fact, maybe that's an easier way of seeing it. Once we conclude, and this is a valid conclusion, so maybe we frame it differently. We say, okay, how many 2, 3, 4 arrows can you include on 9 arrows? So if these are both 9, how many of these coloured arrows can be 2, 3, 4? And in each instance, it's a maximum of 1, isn't it? So there must be a 1. There must be at least 1, 1 on those arrows, and there must be at least 1, 1 on those arrows. So anything that impinges on the ability of us to put 1s on these 9 arrows, we have to pay careful attention to. So if you do end up with a 1 here, a 1 here, and a 1 here, you know there's a 1 there. You know there's a 1 here. You know there's a 1 here. And then you can sort of see that the green and the red can't have a 1 on them. And that's a problem. But it is complicated. It is complicated. Now, but what does this mean? This means this is an 8-9 pair, which means I can take 8 now out of these squares. Wow! I managed to take 7 out. So these now are an 8-9 pair. This is a 6-7 pair. And then there's now a 2 on this arrow. And there's a 2 on these arrows as well. And what does that mean? That I don't know yet. Let's think about that for a second or two. So I know that these are 8 and 9. So now, in one instance, so imagine this was an 8. You've got 2 lots of 1s on its arrows. So there now is a 1 in one of these 2 squares. I think that's right. That's quite... right. Okay. So there's a sort of weird geometry thing going on there. So let me explain what I'm seeing there. Because imagine this was 8. Then we know there's a 1 on this arrow, there's a 1 on this arrow. But we also know that there's a 1 on that arrow. But that arrow couldn't be in these 2 squares because then there would be 3 1s in 2 Sudoku boxes. 1 here, 1 on there, and 1 on there. And that's going to mean there's too many 1s in at least one of those Sudoku boxes. So if this is 8, there's a 1 here. Now that 1 is really cool because it sees the whole of that arrow in its column and will force this arrow to be 2, 3, 4. Oh, this is... Oh, is this too... Oh, hang on a minute. I've thought of something else here. Right, this square is not a 1 in the grid. That one. That square there. Actually, that's a horrible colour. Yellow. I'm going to use yellow. That square is not a 1. I think. So what I'm seeing now is imagine this is 8. That plonks 1 here, which plonks 1 in there because this arrow has got a 1 on it. This arrow can't have 1 on it, so this arrow does have 1 on it, and that 1 must be there. And that sees this square. But the alternative situation in the world by symmetry is that this is 8, which means these 2 arrows have 1 on them. This arrow has a 1 on it, but it can't be here. So that's a 1. That has to be 2, 3, 4, which means there's a 1 on this arrow, but there's a 1 in one of theirs, so there's a 1 here. So either way round, there's either a 1 in this position in the final grid, or this position. And those squares see that square, so that is not a 1. Which means there is a 1 in column 8, in box 9. Now, does that work the same way with 2? Because then I could get a 1-2 pair. No. No, it doesn't, does it? Because whichever one of these is 8 doesn't have to have... In fact, it wouldn't have 2 on both its arrows. One of its arrows would be 1, 3, 4. Yeah, maybe that's a better way to think about it. So whichever one of these arrows is 8, because its 2 arrows couldn't have the same composition, it's going to have a 1, 2, 5 and a 1, 3, 4 arrow, with 1 being the common digit. She's going to put a 1 in one of those squares. The 1 in one of those squares causes a 2, 3, 4 in one of those squares. I can't quite see what that's doing. I'm so sorry if this is obvious. I have a feeling it might be now, actually. That 13 cage can't be 6, 7. So that 13 cage now is... There's a virtual 8, 9 pair in the column, because this is either... Because this can't be 6, 7, this is either 5, 8 or 4, 9, and therefore it's definitely got whatever this isn't is in here. So it's got orange in it. Ah, that might be interesting. So orange, which is whatever this isn't, is in there. So... Oh, well, that's it. Yeah, that's beautiful. That is absolutely beautiful. That might be my favourite bit of an already brilliant puzzle. Yeah, it's this cage now. Right, so look, orange in this box, where does it go? And the answer is, I haven't got a clue, but it's in one of those squares. So what would happen if orange was 9? If orange is 9, then we've got an orange in one of those, an orange in one of those because 22 cage has a 9 in it, and an orange in one of those. And we can't put orange in row 6 at all. We'd have too many oranges in rows 4 and 5. There should be one orange here and one orange here, and there would be 3 oranges in these 2 rows. So this must be an 8, I think. Which is going to knock 8 out of here. Is that definitely right, or am I going crazy? If orange was 9, it's definitely broken, yeah. Orange is 8. So this is a 5-8 pair. This is 9. This is 8. This 22 cage now hasn't got 8 in it, so it is 6, 7, 9. There's an 8 down here. Okay, but then we can... Yeah, now, okay, we can go back and work some magic now. I can see what magic we can work. Let's work some magic. Right, so now green and red have 1 on both of these arrows, which means there's a 1 in one of these and there's a 1 in one of these. So there is no 1 here, and this is a 1. And if this is a 1, that is a 2, 3, 4. And if that is a 2, 3, 4, there's now a 1 on this arrow because it can't also be 2, 3, 4. That's not 1. There's a 1 in one of these because this is 6 or 7. There's a 1 in one of these. This is a 1. And now there's a 1 in one of these. Now this 10 cage is not able to be 2, 8 or 1, 9. So it's either 3, 7 or 4, 6. Now... I don't know, but well, I might label these up actually, because either this is 6 or 7, so the actual choices are relatively limited, aren't they? This has got to be 1, 2, 3 or 4. This is either a 3, 5 pair or a 2, 6 pair. This domino has to add up to 8. 4, 2, 3, 4. Wow, okay. Where are the blue digits in this box? That's a very interesting question. That is a very interesting question, because the blue digits can't go in their own row. They're not equal to 6 or 7. And how many of them is it legitimate to put in a 17 cage? And the answer I'm going to claim is 1. You can't put more than 1 in, because even if you put the 2 biggest ones in, 3 and 4 say, the other digit would have to be a 10 to make it add up to 17. So these digits are those digits. Well, no, 2 of these digits to be precise are those digits. Which means this can't be a 1. We already knew that. So this is from 2, 3 or 4. Yeah. Oh, right. Now look at this leg of the 8 arrow. This 8 arrow can't be 1, 3, 4 anymore, or both of these digits would be 2. So this is 1, 2, 5. And we know this can't be the same, so this is 1, 3, 4. There's no 2 up here anymore, so this is a 3, 4 pair. This, we know that this arrow's got 1 and 2 on it, so the 1 and the 2 are there. There's no 2. Right, this domino adds up to 8, and it doesn't use 1 or 2 now. So that's 3, 5. Which means that's not 3. That's a 4. That's a 3. Now this arrow adds up to 6. So that's a 6. This hasn't got 4 on it anymore. So this is a 2, 3 pair, therefore 3 on that arrow goes there. This isn't 2 anymore. This is a 1, 4 pair, which means that's a 5. And we suddenly are... That's a 1-2 pair, so that's a 4. This is a 2-3 pair. This is an absolute worldie, isn't it? It is brilliant. It is hard, though, actually. It is definitely not an easy puzzle. Can I use the secret up here? 17, 27, 30, 14. Yes. Okay. Look at this box. Now, this is a secret I share with only my very favourite people. This is if I was a one-trick pony, this would be my trick. The secret is that a whole box of a Sudoku sums to 45, believe it or not. That's what the digits 1 to 9 sum to. Now look, we've got 17 there, plus 6 plus 4 is 27, plus 3 is 30, plus 1 is 31, which means that to make the whole box add to 45, those two squares have to add up to 14, and they don't use 6, so they're not 6 and 8, so they are 5 and 9, and I know the order. 5 and 9 go in. 5 is in one of these two squares by our old friend Sudoku. 5, 6, 7, and 8 into these squares. That's not 8, so there's definitely an 8 up here, so that's not the 8 digit. These squares are 2, 7, and 8. That feels like it should be interesting, doesn't it? Yeah, it is interesting. That's got to be a 7 by Sudoku. So I get a 2-8 pair here. I can do that. I get 2 in the corner. I feel like singing about that, but strictly it doesn't involve getting a song, does it? Right, what about... Where's 9 in row 1? It's there. So these should be a 6-8 pair. And these are a 6, 7, 8 triple, and that's a 7 by Sudoku, so this is a 6-8 pair. Now we're going to get this one, aren't we? Because we have not put 4 and 5 into row 2. So this is 4 and 5, which means that's 8 by mathematics. This is 6. That's fixed this. That's now 3 and 7, not 4 and 6. Which means this is 2, this is 3, this is going. There's a 2 on this arrow. I now know it's in yellow. Which means this is either 1, 3, which it's not. So that's a 7. And 6, 7, 8, 9. They were all different. It was just very hard to show that was what was going on. That's 1, 4. So this is 4. This is 5. And okay, I've not put 8 and 9. Oh, I can do it. That's 8 in column 8. That's 9. That's not 9 anymore. There's definitely a 9 in here. So that's 9 by Sudoku. 9 lives in those two squares. This square is 6 or 8. There's a 6, 7, 8 triple there, so that's got to be a 5. That's got to be an 8. That's got to be... Oh, actually, hang on. Why did I think... Oh, no, that's right. Okay, that seems fine. Actually, I'm just going to go back. I'm not sure. Why did I think... That 9 I felt comfortable with. What did I do then? I pencil marked 6 and 8 there. It just feels like this triple unwound incorrectly. I'm not sure I trust that. In fact, it's better if because that square is 6 or 7 according to actual pencil marks. And that makes this square 8, which makes this square 8. Is that what I got before? Maybe it's the same thing I got before. I don't know. But something felt wrong there. And although it doesn't seem to have made any difference. 6, 7, 9. This is 3, this is 7. So that's 3 and that's 2. What now? 4 and 6 into that column. Yeah, I can do that. 4 goes there, 6 goes there. 7, 6, 7, 6. This 4 is useful. That does 4, that does 1. This is 6, this is 8. 8's not on this arrow. I'm not sure if we expected that or not. Probably. Oh no, we couldn't have put 8 there because that would have been a 9, and it can't be a 9 for some reason that we worked out earlier. 1, 5 into, oh, where's 5 in row 5? It's there, so that's got to be a 1. This digit I should be able to do. That's a 7. That's a 2, that's a 1, that's a 1, that's a 4. It should be 2 and 6. Oh, bother. No, okay, I can't do that. 2 and 6 don't work. But these squares are 3, 5, and 9. And that's not 3. And this column, okay, let's see if we can do better. This is 4 and 5. Yeah, I can do that. That's 4, that's 5, so that's 9. These squares are 6, 6 and 9. I can do that as well. 6, 9. So these digits are going to be the key, I think. 6, 7, and 8. So well, it's sort of a thermometer type thing going on. The maximum difference between these digits is 2, isn't it? So that's got to be a 1 or 2, and it can't be a 1. So that's a 2, which makes that an 8 and that a 6. That's lovely. That's a lovely idea. That's an 8. This is a 7. That's a 7. That's a 9. That's a 2. That's a 6. I need 1, 3, and 4. So that's a 3. That's a 4, and that's a 1. And that's a 2, and that's a 1, and that's a 5, and that's a 3. If this doesn't work, I'm going to cry. 1 and 5 go like that. Oh, I didn't get a 3 in the corner. No. 4 and 9. I had a good chance as well. And this is 2 and 3. Good grit. That is a brilliant puzzle. Is it right? Yes. That is absolutely brilliant. My goodness me, arbitrary. I think I've done a couple of arbitrary puzzles before on the channel, and they're always absolutely sensationally good. And that is another one. That is bonkers. It's bonkers. I'd love to know whether the thing I did in the middle there to prove these weren't 9s, whether that was what I was meant to do. I think it might have been. I loved the way you could trace them through the grid and see what happened to 1s. Now, hang on, let's tidy up our colouring, otherwise people will get cross with me. So if I double click 8 and do that, that should work, shouldn't it? And get rid of 2 doesn't really, get rid of this, get rid of these. In fact, I'm sort of I'm making it all a little bit more Spartan, which is a bit of a shame. But anyway, absolutely brilliant puzzle. Loved it. Let me know in the comments how you got on. I enjoy the comments, especially when they're kind. And we'll be back later with another edition of Cracking the Cryptic.